Alright, something doing something. Can you see that, or do I need to make it bigger? Okay. Alright, so, chemical bonds. Where we left off last time is we talked about Alright, the periodic table and ions and oxidation. We talked about oxidants and antioxidants. So, the way oxidants and antioxidants work is that they are attacking chemical bonds in some way. So there are 4 different ways that we can have 2 molecules interact with each other. The first 2 you're probably super familiar with, and the next 2 maybe less so, depending on what kind of high school chemistry you took. So the first one is a covalent bond. When electrons are shared between 2 atoms. Now, so for 2 atoms to share electrons, the atoms have to be close enough for the electrons to be attracted to both nuclei. Alright, so thinking back from last time, right, the center here, there's my nuclei where it's positively charged because it has protons and neutrons in it. These guys out here are the electrons. Alright, so you got your minuses circling around the outside of your pluses. So for these 4 minuses to be shared, the 2 atoms have to get close enough that both this plus attracts them and this plus attracts them. So he'll be out there for hours. He's chatty. Okay, so elements like hydrogen or oxygen or carbon or nitrogen. Our big guys over here, right? C, O, N, H, those guys. All nonmetals, also true. Those guys tend to form covalent bonds. And of the 4 bonds we talk about, covalent bonds are the most stable. It takes a lot of energy. Once these guys are shared, it takes a lot of energy to push them back apart. That's a super stable arrangement. Hydrogen bonds is different. Hydrogen bonds are a separate category. Hydrogen bomb. Yes, a hydrogen bomb is a tricky thing. It is breaking apart covalent bonds, which is why they release so much energy. What's that? Fission is when you break apart an element into other elements. So that's even more energy. So you're saying, I have a piece of uranium, and I'm going to hit it so hard the uranium itself breaks apart. A covalent bond, I have 2 uraniums, and so it's going to take quite a bit of energy to break the 2 uraniums apart, but it takes even more energy to break apart a uranium by itself. Alright, so it takes a little bit of energy to cut off your arm, but it takes a lot more energy to blow you up from the inside out. I mean, just think about it. It would take a lot more work if I was going to slice you all apart versus just taking off an arm. I was watching a little bit. Do you guys watch the show Luther? Luther? Do you guys like Dexter?
Yeah.
Okay, Luther is kind of a British version of Dexter. So, anyway, that's what they were doing on the show last night, so it's on top of my mind. Neither here nor there. Otherwise, the lady's thigh won't be. Yeah, obviously. I mean, seems like a gimme. What was that? I know, this is going to be on YouTube, which is why I probably don't have a lot of subscribers, because I ramble on. We eventually get to the chemistry, but you'll find that I spend a lot of time with pop culture. I just love it. So I love watching TV, music videos, whatnot. I was just watching Ed Sheeran's music video a few minutes ago, the Don't one. I'm like, I could watch that one over and over again, the guy dancing around. And if you haven't seen it, he's a pretty amazing dancer. I mean, he just, it's like he doesn't have any bones. It's all wiggly. Alright, so those are my two examples that you can't see. There we go. So my two molecules that have covalent bonds would be water. Does anyone recognize what this guy is? You may not. Sugar. Glucose, sugar. Yeah. Glucose is a sciencey word for it. Sugar is like the normal version of it. Alright, so then let's talk about ionic bonds. I use bonds in quotations because it's not exactly the same as a covalent bond, right? So if you're thinking of a bond, not a James Bond, but like a regular bond, it's sharing electrons. Ionic, quote-unquote, bonds don't share, they steal. So, an ionic bond is when electrons are shared unevenly between two electrons, or two atoms. So of one atom taking an electron away from another atom, and not giving it back, taking it in. So it's kind of small on your page. So I have sodium here, and I have chlorine. The sodium is going to, I guess you can see it either way. The sodium is either giving away its electron or the chlorine stealing the electron. So in this case, they both start off neutral, right? Zero charge. If the sodium has given away an electron, what charge does it have now? Right, positive, given one away. And the chlorine has gotten one extra, so he becomes Cl minus, which is negative. Now, they're not sharing electrons, right? What is going to keep them in close proximity to each other? Right, they're opposite charges. So by doing this, it's like a bond in that they are now stuck together. But it's through one giving away an electron, not sharing anymore. And we have two atoms that are stuck together by opposite charge. So I've now made this NaCl guy, right, one sodium, one chlorine. What's that guy called normally in regular? Right, that's just salt. So salt has ionic bonds. Sugar has covalent bonds. A little bit of delay. Good so far? The to see, maybe this seems vaguely familiar from other classes. All right. All right, so then we have two more types of bonds that again are not exactly bonds, they're more interactions. So polar interactions, also hydrogen bonds kind of fall into the same category. So polar interactions form between two different molecules for a temporary, we're going to call it bond in quotation marks too. It's something that sticks them together for just a little bit. The polar bonds form between these two molecules. Where the molecule has a positive end and a negative end. Alright, so my covalent molecule, everybody was even, perfect even sharing. My ionic molecule, uneven sharing. Definitely one stole it from the other one. In a polar, one molecule is trying to steal the electron, but is not successful at it. So, if I'm looking at, what's a good example I can use? Let's use we can use water. Yeah, that's fine. We can use water. I have my water molecule down here. So here I have my water molecule, and the oxygen is trying to steal the electron from over here. It's also trying to steal one of these electrons or one of those electrons. Doesn't matter who from. It's trying to pull it to it. And so by doing that, it ends up with being a negative end. And so since these hydrogens are having the electrons trying to be ripped away from it, all these hydrogens end up being a positive end. The oxygen is trying to steal the electrons away. Like we talked about last time, oxygen loves everybody else's electrons. So it's trying to steal them from everybody. And these hydrogens are like, please don't take it. And so they end up being slightly positive because they're not very strong. So they don't have a great grip on their electrons. So it's kind of headed towards the oxygen, but then they pull it back. And they give it away. And then they pull it back. Now, and that's what these little symbols mean. That little delta. Are you more familiar with like this big delta? It means change in. Right, the big guy, this is delta. That's capital delta. Change in. Like we usually talk about when it's like delta T or delta something else, that means change in. Lowercase delta in the Greek is that guy. And it means little change. The big delta means big change. Little delta means little change. There's your one Greek letter of the day. You guys know any of the others? In college we had to learn how to sing the Greek alphabet. Because I'll sing it later. Alright, so okay, lost my train of thought. So let's see, negative ends, positive ends, delta, okay. So our elements O, N, and F, right, are oxygen, nitrogen, and fluorine. They really, really, really want everyone else's electrons. So here's an example, right? Here's my oxygen trying to steal the hydrogen's electron. Oh, finish my thought. And hydrogen is willing to donate an electron. We often see molecules with O or N or F. Is temporary? Is it temporary? Is that right? Temporary? So we often see molecules that contain either an oxygen or a nitrogen or a fluorine interacting strongly with a molecule that has an H somewhere in it. So in this case, I have water, right? Water has an oxygen interacting with this water with an H. Or it could be, let's make up this molecule. We'll call it interacting with water. Alright, so is this fluorine going to try and interact with the oxygen or the hydrogen? It's going to want to go after the hydrogen, because this is going to be a little negative, and this guy's going to be a little positive, and that guy's going to go after that hydrogen. So it's going to be not an actual bond, but it's going to pull it towards it, trying to get the electron off it. So these are fairly strong interactions, right? Covalent is super strong because we are full-on sharing. Ionic is pretty strong because we have opposite charges. This is like one step down from that. Not full charges, not full sharing, so moderately strong. I have a lot of colors, they don't really mean anything. I just get tired of writing all in one color and then I just change my mind. Okay, let's talk about the last one, which you can see I don't leave very much space for because it's not very important. But it is one of the 4 forces. And it's called van der Waals forces, obviously after Dr. van der Waals. I need to invent something like this, otherwise I'll never get something named after me. So van der Waals forces occur between all molecules all the time. So all molecules experience van der Waals forces. It just means that if 2 molecules are in close proximity, they kind of pull together for a minute to see if they will be attracted, and then they're like, nope, then they wander off. Or they're like, maybe. So it's kind of like a dating app, right, where they kind of look at each other and like, maybe, oh, no compatibility. One wander off, and then another molecule comes in. Compatibility. And maybe it's like a dipole force, where it's like kind of compatible, but not really. No one saw. Or it could be covalent. They're like, yes, we can do this, and they get married. Just like that. I think that's actually what happens, probably, on the molecular scale. Alright, any questions about our 4 types of molecules? Or molecules, 4 types of interactions between molecules. Alright, in this case, let's talk about some energy. So, energy obviously relates to this class because cooking or baking or boiling or anything like that, right, is an input of energy into whatever you are making. And that input of energy, through cooking or baking or boiling, forces these bonds to break and reform with something else. So, let's see how I want to do this. Alright, so the more energy a system has, it does. I just go to sleep. Oh, there we go. Oh, there we go. Alright, so the more energy a system has, I'll probably just have to turn off the screensaver. The more likely I guess I'll call it a chemical change will happen. Alright, so you can think about this when you are baking something. Let's say you're supposed to bake your garlic bread, right? Your frozen garlic bread, it recommends 450, and it says 10 minutes at 450. What if you forget to set it to that and leave it at 350, the default on your oven, and what will have happened in 8 minutes? Nothing, right? It'll still be mostly frozen. Right, so the more energy, so the more heat you're putting into it, the more likely it'll be toasty, melty, the way it's better to eat. I guess you could eat it frozen. If you were desperate, I guess. So, the more energy, the more likely a chemical change will happen. So, obviously a stove puts energy into your system in some way, right? Either you're going to use the oven part and bake something, or you're going to use the little stovetop part and like boil or saute or whatnot. What is a refrigerator doing that's important? It's taking energy out of the system, right? It is removing the energy from your food, cooling it off, which is why if you ever stand real close to your fridge, it feels hot on the outside. It's because it's sucking that heat out and blowing it out the exhaust, depending on your fridge, either at the top or at the bottom. So your fridge feels hot on the outside because it's sucking all the energy out of your food to keep it cold. Because your food had energy, like at room temperature, what happens to your food at room temperature if you leave it for like a day or two? It gets all kinds of moldy and gross, right? Because it has the ability to grow other things. So if you take away that energy, you can't grow anything. Okay? So let's talk about types of energy that molecules, especially food molecules, have. Alright, so we all hopefully know our two types of energy. We got our kinetic and our potential energy. Alright, kinetically is when you have motion. Potential is when you have position that gives you the opportunity to have some sort of energy. So, we're thinking about atoms or molecules. They have the ability to move in space, as well as vibrate and rotate. So if you're thinking about your molecule in three-dimensional space, right, it could move. If I was holding my molecule, I could be holding it here, or it could move all the way to the end of the room, or it could come back, or it could stop anywhere in between, right? It has energy of motion. It could also just stay right here and spin like this. Or it could also stay right here and vibrate up and down. Turns out molecules do all three all the time. So they are vibrating, rotating, while moving in three-dimensional space. If you can think about that picture. No, okay. Just do one at a time then. One at a time. But they are actually doing all three all at once. Yeah. Some people are good at thinking of 3D pictures, and some people not so much. So higher temperature. How much energy do I have if I am hot compared to cold? Right, I have more energy if I'm hot. So at higher temperatures, I've given more energy to the molecule. So they are spinning faster, vibrating faster, shooting through space faster. They're doing all three things faster than they would be if they're cold. Let's call that motion, faster motion. So when I go to boil my water on top of my stovetop, I am giving more energy, which is temperature, to my water, what happens to the water as I impart more energy into it? It gets hotter, and then eventually starts to do what? Boil, which is going from water to steam, right? What if I am putting pasta into my water, right? So now I have hot water, and I put room temperature pasta. What happens to the pasta? It gets hotter, right? So it's getting hotter, and so if it's getting hotter, I'm giving energy to the molecules in the pasta. If I'm giving molecules into the energy into the pasta molecules, if I'm putting energy into the pasta molecules, they are also going to change in some way. They're going to start moving faster and faster and faster, and eventually they can start breaking some of these bonds they have related to each other, right? Because when you put the pasta in, it's hard. If you boiled it, you have broken some of the bonds and caused it to soften up. So you have to give it enough energy to start breaking some of the bonds that are holding it stiff. Now, as molecules move faster, otherwise known as getting hotter, right, so as you move faster, you gain some sort of force, like you're able to, imagine you're a driving car, right, so your car is going 20, and it hits a brick wall, mostly smushed. If you hit a brick wall at like 200 miles an hour, you'll probably break through it. So the more energy, the more motion you have, the more force you have along with your motion. You then have these collisions between molecules, right? Because you're saying they're moving in three-dimensional space. They're going to eventually bump into somebody else. So now they're bumping in harder and more often into each other. So the collisions increase, which causes bonds to break or form. Because in some cases we want them to form. So if you're thinking about like your cake batter, right, you've made brownie or cake mix or something like that, like it's all just kind of liquidy, you want to form bonds in that one. So you're going to impart energy in it so that they all start to link together. You have a solid cake if everything goes right by the end of it, rather than, otherwise you just have cake batter, which is delicious. I would just eat it by itself, but you could probably want to also make into a cake. It's less salmonella issue if you actually bake it into a cake. Plus the icing sticks better to the actual cake rather than just icing on. Not that I've tried that, but it's hard to ice just a spoonful of cake batter, unless you have spray icing, in which case no problem. No, or whipped cream. Whipped cream's good on too. Good there. Good energy so far. Okay. In that case, let's talk about bond energy and my super incredible graphic. Look at that, two balls with energy breaking a bond. I don't draw very well, so that's the best I could do. Circle, circle, breaking a bond. Alright, so energy. Alright, so if I have a really strong bond, so I'm talking like covalent bonds are the strongest. I've already said that. The stronger the bond, the more energy needed to break it. So, if I'm talking about covalent bonds, so if I have a strong bond, it's not going to break really at room temperature. That's the point of it being strong. The covalent bonds should rarely break at room temperature. otherwise would bake everything by just sitting it on the counter, which would be awesome. Save me a lot of effort if I could just, put my meat out on the counter and be like, done, cooked. I guess if it's like sushi or beef tartare, then yes, technically it's what it's eat. But most people don't eat it that way. You mostly cook it in some way. And so, need to add energy in the form of heat to break these bonds. What if I have some weak bonds, like the one we talked about here, van der Waals forces that occur between everything, or these polar interactions? I'll say especially van der Waals. That's mostly what this refers to. They are constantly breaking at room temperature. So, let's say for instance, let me draw you an amazing sketch, and then do a quick example. Alright, do this and that. Alright, so we haven't gotten to this part yet, but go with me and says what this looks like. It looks like a jellyfish. That's a fat molecule. That's what a molecule of fat looks like. It has a special kind of head, and then it has these long chains of carbons hanging off the bottom. Yeah, like a triglyceride. That'd be true. That'd be the glyceride part. Anyways, these are fat molecules. So imagine this is a really zoomed in picture of butter. And this is one butter molecule, and this is the other butter molecule. Okay? It looks like two jellyfish hanging out, but butter. It's actually butter. Butter. So we have this butter molecule and this butter molecule, and they're going to interact with these van der Waals forces, which means they're going to come close, see if they can make a bond. They can't, so they wander away from each other, and they come closer. So those are very weak forces. So if I keep these molecules cold, so imagine the butter in your fridge, how stiff is it? Well, it's pretty stiff, like it takes a good effort with a knife. So you're going to force them to kind of be like, no, you just have to stay here. Right? What happens if I'm at room temperature? If I put my butter and I let it sit at room temperature for a while, it melts, right? It thaws out, melts out. These butter molecules will go to where they want to be. They don't want to be real close to each other because there's no attraction. So they'll go to the opposite sides and they'll melt. Right? So, in fact, what happens to if I have like a spoonful of butter and I let it sit at room temperature, does it all still stay in the spoon? For the most part, but is it a little tiny clump or is it spread out amongst the spoon? Right. Right, so it kind of spreads out. So in fact, they will break apart so far that they're actually going to spread out and become a liquid, push apart as far as they can. What if I then put that tablespoon of butter, into a hot pan? It's going to spread out even more, right? And then it actually starts to boil, assuming you have a reasonable temperature. So, it doesn't take very much energy to get butter to melt or boil. So, things like fats and oils have very weak bonds, which is why they're great for cooking, that they are easy to break apart amongst each other. Yes. No.
Do the types of bonds that like jellyfish do interact
Mhm. Yeah. Yeah, we'll talk about that. So, like for a very generic example, I'll sketch it here. So, what's a good example? Oh, protein. We'll do a protein. So, a protein is an amino acid stuck to an amino acid. We'll do a better sketch next week. Right, so we have a very short protein. It's 3 amino acids stuck together. Your body has the ability to break these amino acids apart and reuse them for other things. But we can't process all proteins. So depending on what the combination of amino acids is, sometimes your body can break them apart, sometimes it can't. Oh, an even better example. Let's talk about alright, sugar versus cellulose. So cellulose is a version of sugar. It's a bunch of sugar molecules all stuck together in a long chain. So it's really sugar, sugar, right, something like that. Your body has no problem digesting sugar. And you would think, no problem digesting this. We don't have the ability as humans to break the bond that's holding together the 2 sugar molecules. In fact, no mammal has the ability to do it on their own. So like animals like cows and whatnot, they have to have bacteria in their stomach that breaks that bond for them. And then they can use the sugar. Yes, the bond. We'll talk about that a lot more. I have a whole thing about cows and ruminants and what's the difference between cow milk and buffalo milk and bison milk and you'll be super knowledgeable all that kind of stuff here in a little bit. Then we're going to talk about cheese. Eggs, whole chapter on eggs. Eggs are fascinating. Did you know an egg, by the time it's laid, is 30% of the chicken's body weight? So it just pops out a third of its own body weight and then just gets right through it again. It is crazy. Yeah. Because, I mean, imagine pooping out a third of your own body weight every 21 days. Pretty crazy. I bet it's a relief. But at the same time, ridiculous. Yeah. Yeah, well, it depends on how you're counting it. So it depends on when you consider the conception of the egg. Right, so chickens can lay eggs every day, but it takes about 3 or 4 weeks to get to the point that they can lay the egg. Yeah. It is crazy. And they kind of get into a cycle.
Yeah, and then they have like 40 eggs.
Yeah, I don't really eat eggs. I wish I liked them. I don't really care for them. Okay. I'd rather eat Lucky Charms or something than eggs. Bad health choice. Terrible health choice. But deliciousness wise, Lucky Charms is good. Alright, so I am sure everybody's probably familiar with our 3 phases of matter. My little gas guy kind of fell apart. Do you want me to define the 3 phases of matter? You guys feel fairly confident you could identify a solid and a liquid and a gas? Alright, we'll skip ahead then. We'll talk about other phases of matter. Right, so those are the 3 obvious ones. Solid, liquids, gases. My cute little picture over here. There is... Here we go. There is one other state of matter that doesn't come up very often, which is a supercritical fluid. plasma could be a fluid matter. It's technically a supercritical. It's kind of in between. I'm picturing a phase diagram. Phase diagram is over here in this part. We're kind of in between phases. It's kind of looking kind of gassy. But, so, supercritical. Fluid. Where it's acting like a liquid and a gas at the same time. Pretty cool thing. So, dry cleaning is a supercritical fluid. That they put the dry cleaning fluid at super high pressure so that when it goes through your clothes it acts like a liquid and that it flows, but it's actually a gas that under the high pressure it captures the dirt molecules, passes through your clothes, and then they release the pressure and turns it to a gas and drops the dirt. That's the same way they decaffeinate coffee. Really high pressure carbon dioxide passes through the coffee bean, it captures the caffeine molecule, pulls it out, and then they release the pressure, and it becomes carbon dioxide becomes a gas and drops the caffeine on the floor. You can buy just powdered caffeine. You shouldn't ever ingest powdered caffeine by itself, but you can buy a 1 pound bag of caffeine powder. They sell it, or sometimes they use it to caffeinate other things. So, like a little known fact, orange Fanta is actually caffeinated. So you would think an orange soda wouldn't, because it's not a cola, right? But they put the powdered caffeine in the orange Fanta, so it's actually a caffeinated drink. Or some of those other, Red Bull or whatnot. That's all it is. It's just caffeine powder and water, and bubbles and color, whatnot. So, okay. Alright, let me do this one last thing on this page, and then we'll save the last page and start something else. Oh, there's no more pages. Oh, good. We'll do this one last thing then. Alright, the foods and states of matter. Okay, we don't often talk about your meat, right? If you're going to cook chicken, we're not talking about chicken going from a solid to a liquid to a gas. Probably not. It means you've probably way overcooked it if it's turned into a gas. Gaseous chicken. Right, so those are physical changes, right? If we go from here to here to here, that's a physical change. We are more often talking about chemical changes when we talk about food. Alright, so a chemical change is a change you can't undo. So when you cook the chicken, you have undergone a chemical process that you can't undo. Right? You can't turn the chicken back into raw chicken. And you can't unbake a cake. So you've done a chemical change that is not possible to reverse. So these chemical changes. Okay, I'm going to stop there. I have like 2 or 3 more thoughts on this, but I will save it for next time. For Friday is just regular BCC class. We're just going to talk about, Megan's going to be here, we're just going to talk about regular BCC stuff.